Hi everyone. So we're going to continue our discussion on friction. On Today we're going to look at friction on an inclined surface. Previously we looked at friction and how it behaved on a horizontal surface. And we had a little diagram here showing the weight of an object and the normal force, equal magnitude, opposite in direction to the object's weight. And this normal force is always perpendicular to the surface that the object is resting on. And yes, it is equal magnitude to the weight, but as we change the angle of the surface that this box rests on, all of its weight is not directed in the opposite direction. It's actually going to be shifted a little bit more towards the vertical. This is where we're going to look into resolution of vectors and how we can take that weight vector and see which portion of its weight is actually going to be pulling it down the incline. And we can resolve that weight into two different components. We can resolve it into an unlimited amount, but we focus on just two components. The one that's parallel to the inclined surface, so that's going to be a force that is parallel to the inclined surface, and another one that is perpendicular to the surface. So we'll look at another one here that is created at a right angle to the surface there. And that's going to be our force right here, which would give us our perpendicular angle. Now the component that I just drew there, the component that is perpendicular to the surface, and I should probably adjust this here. This is actually our FG. This is going to be our perpendicular component of our weight. That was mislabeled on my part. So the component that is perpendicular to the surface doesn't have any effect on the motion of the object, because the object can't move through the ramp. So the object cannot move in the direction of that perpendicular force. It can't move in the direction of our perpendicular portion of our weight, which is also going to be known as the x component or the cosine component of our weight, which we'll see we can represent as Fg cosine theta. Now the component of the weight, the parallel portion of the weight that's parallel to the inclined surface, is what actually tends to accelerate that object down the incline. And I'll put this all together in a diagram in a minute. We'll take a look at that. And we saw this the other day with the demonstration I did in class with the slope ramp and the horizontal ramp and how that cart actually moved. So as the angle increases as a ramp, if we consider two different ramps here, one that is pretty sloped and the other that is very steep, we are going to, if we have boxes resting here, we actually change how much of our weight is pointing down the ramp or straight through the ramp. So the component of the weight parallel to the incline increases as we increase that angle. We can call that angle theta. This would be theta underneath there. And if the component of the weight parallel to the incline goes up, the acceleration down the incline is going to increase. And we saw this as I tipped the ramp further. We overcame that static friction. More of the weight was put into the vertical component of the vector of our force, and the block accelerates down the ramp. Well, the force of friction between these two surfaces is directly proportional to the normal force, which we know as F sub n. And again, that is equal in magnitude, but opposite in direction to the perpendicular component of the object's weight. And we're going to find that that force of friction, let me do a blue here, is going to make a right angle here with the perpendicular component of our weight, but will be opposite in direction. So it's going to oppose our motion. Now, as the angle of that ramp increases, the component of weight that's perpendicular to the incline gets smaller, or decreases. So we shift the amount of that weight that is pointing through the surface to pointing down the surface, and the friction force decreases, goes down, which ultimately, as we get steeper, makes that block more and more likely to slide down the ramp. The steeper we make that ramp, the greater the acceleration we have of that object down the incline. And I'll show this to you in a diagram. Let's do that after we talk real quick about rolling and fluid friction. So rolling friction, you guys have seen a couple different examples of rolling friction. We've talked about a couple. Recently we discussed a problem with tires locking up during a skid on ice, which is why we use anti-lock brakes, is to prevent that tire lockup. So we don't have kinetic friction with tires that are locked up. We would prefer to have some kind of rolling friction. If our wheels are rolling on ice, they're going to have less friction than if they were not rolling on ice and the car was just kind of sliding across the rubber without the wheel actually turning. So in general, given that example, rolling friction is usually less than sliding friction. So wheels that are going to be rolling are going to have less friction than wheels that are just getting pushed forward. And I think of this that if you were on a bike with your handlebars here, and you're riding your bike, you'd rather have those wheels rolling as opposed to the brakes being locked up and this tire just kind of skidding down the road. We'd want these wheels to be rolling. Otherwise, it makes the bike much harder to get down the road. Now, fluid friction, anything if you think of yourself swimming, or those of you that are swimmers that do diving, we have fluid friction anytime an object moves through a fluid. And this is also, we can consider air as a fluid as well. And that friction really is going to depend on the surface area of the object, as well as the speed of the object moving through the fluid. Now, a swimmer that swims faster through the water would have more friction with the water as opposed to a swimmer that is moving slower. Same idea with a airplane moving through the air. A smaller plane has less surface area, which reduces friction, reduces drag. the faster the plane is moving. The more friction we have, more heat that is produced, the greater the effect on um, things like fuel economy. We always hear that the faster that you drive in your car, the lower your fuel economy is as you try and not only push your car along the road, which increases friction, increases your heat production, but you're also moving through a fluid as you try to push that car through the atmosphere. These are all non-ideal scenarios that reduce your overall fuel efficiency. So I'm going to give you a little diagram here, a free body diagram of an object on an inclined surface, and this should be used, well, it's going to be applicable to all of our inclined friction type problems, and this should be used as kind of a cheat sheet for any time you come across one of these problems. So I'm going to start with a box here, free body diagram. We got an object there. I like to put a little circle in the middle to indicate the center. Now we have a few different forces here. I'm going to start with our normal force, which is opposing our weight. It's an opposite direction of our weight, equal magnitude, but it is perpendicular to the surface on which the block is on. Now our weight always points straight downwards. And we'll label that as our weight or force due to gravity. Now, opposite our normal force, bring this down. This is going to be the component of our weight that is perpendicular to our surface here. And this is going to be the x component of our weight, or Fg cosine theta. Now the portion of this weight that's going to bring this block and accelerate this block down the ramp, it's going to be the component that is parallel. And it looks like my diagram is a little bit off here. I'm going to try and keep this somewhat consistent here. I use that color. Let's come down to about here. The component that is parallel to the surface, this is our vertical component, although it doesn't quite look like it. I'll show you in a second why it is. This is the vertical or sine component of our weight. So we've broken this up into an x and a y. And it might kind of help to think of it, if you're having trouble with this, as this is our y direction and this is our x direction. And if we orient that just so and turn this kind of counterclockwise, you can see how that lines up with the horizontal and vertical components. Now we also have this Fg sine theta parallel to the surface here. This is what's going to be the component of our weight that will accelerate us down the ramp. So this is also Fg sine theta. And this is actually our friction force. The angle of this ramp is given as theta. Now if we try to apply a force pulling this box up the ramp, we'll call this F applied, or our applied force to pull the box up. Our Fg sine theta opposing this applied force is our friction force. It's opposing that movement. We also create here another right angle. So we kind of see there the two different right angles that are created here. Now, to show you how these components, FG cosine theta and FG sine theta, can change, we'll look at two different examples here. I'm going to try and draw this as best I can. If we look at a steep incline, we'll call that theta there. And I'll try and do this again in two different colors. So we have the weight of an object, and we will resolve that into two components. Our perpendicular component and our, it's kind of rough, our parallel component. This parallel component, which I can't seem to draw in a straight line, is the other leg there of our triangle, and it is parallel to our incline. So up here, our FG sine theta is parallel to our incline. I don't really like the way that triangle looks, so we're going to redraw that here. Bear with me, please. Our weight's going to come, we'll try and exaggerate this a little bit more, all the way down. We'll do our perpendicular component here, and our parallel component here. I think we can see that's a little bit better. My vectors don't quite point head to head or tail to head, but that's pretty good there. So what this shows is that as our angle increases, our friction actually decreases. Our y component, which we know as FG sine theta or mg sine theta, gets bigger. And the x component, which is mg cosine theta, gets smaller. And that would be mg cosine theta and mg sine theta. So that component's getting bigger, and we'll show that in another example here. And the x component, the cosine theta component, gets smaller. So we shift our weight from pointing down through the ramp to pointing down the incline. So looking at an inclined plane as an angle decreases, I'll do a relatively shallower ramp at angle theta. I'll probably have a little bit of a difficult time drawing this one, but bear with me. We have weight that points straight down. We have, it's got to be perpendicular here. And then we're going to have, that's kind of tough right there. I'll redraw this in class. That one's kind of tough to see unless we can kind of blow this up a little bit, which I'll try here. So we'll extend this out, and we'll go something like that. We'll call this theta. Just doing all sorts of redrawings today. We'll put in our perpendicular component here. And this will be mg cosine theta. And then we'll put in our parallel component, which is mg sine theta. And this one again is parallel to that line there. This is parallel to our y component of our weight. Now and what you need to see here and understand, as this angle decreases, as theta decreases, our friction will increase. It's going to be harder to get that blocked on the ramp because more of its weight is not pointing down the ramp, it's pointing through the ramp. So the friction force is being applied more directly to the surface as opposed to down the surface. So in this scenario, the y component of our weight, again that is mg sine theta, the portion pointing down the ramp, gets smaller. And again, these aren't to scale, but we can see the difference here in the vector of our mg sine theta in the example here compared to the vector here. That y component does get smaller. And the x component, mg cosine theta, gets larger. And this one's a little bit harder to tell, but we can compare that vector there to the vector here. And on the lower angled ramp, our mg cosine theta will be greater than in the steeper ramp. Make sure you focus and review and take a look at, and make sure you understand this diagram. I'll draw another one of these in class. We'll talk about it more in class. This is the diagram that we want to use to try and figure out what our friction force is going to be. And again, that is going to be the y component of our weight that tends to accelerate the block down the ramp, or Fg sine theta. Leave you guys with a joke for today. What is a nuclear physicist's favorite meal? It is fish and chips. Have a great day, everyone.